You've probably heard of the double slit experiment, right? It's famous for being, well, impossible to really wrap your head around. But what if, for over a century, we've all been missing this secret? What if the real mystery isn't about the particle at all, but about the supposedly empty space it travels through?
So this gets us to the heart of it, the classic quantum question. You fire an electron at a barrier with two slits. You'd expect two lines on the screen behind it. Instead, it acts like a wave and creates an interference pattern, almost as if it went through both slits at once. But the second you try to look at which slit it went through, poof, it's a particle in a single spot. So, which is it?
Okay, so the official answer you'll get is something called wave-particle duality. It's kind of this conceptual patch that basically says a quantum object is both a particle and a wave at the same time, and it just picks a side depending on how we measure it. It works on paper for sure, but let's be honest, it feels more like a magic trick than actual physics. And yeah, this really nails the problem, doesn't it? A particle is here, a single dot. A wave is everywhere, it's spread out. In our world, these things are polar opposites. So telling us something is both at once, well, that basically forces us to throw our physical intuition right out the window. Okay, but here's the big question for today, the one we're really going to dig into. What if we've been asking the wrong question? What if the particle is just a particle, always, traveling a single path? And that wave, what if it's not part of the particle at all, but an invisible feature of space itself? So for more than a century now, this whole riddle has kind of pushed physics into a corner, forcing us to accept an answer that, while it works for the math, just doesn't feel real. But what if the key to a real physical picture was there the whole time, hidden in a forgotten idea from a name you'll definitely recognize? Right, the clue comes from none other than Albert Einstein. But here's the twist. It's not from his super famous theories of relativity. No, it's a pretty radical idea he came up with after them, an idea that for some reason history has almost completely ignored. And just look at that date, 1920. This is 15 years after he supposedly killed the whole idea of an ether with special relativity. And here he is bringing it back. He was arguing that his new theory, general relativity, made it obvious that space wasn't just some empty nothingness, it had real, physical properties. It was a medium. Now this is super important. We're not talking about the old ether idea. You know, the one that was this fixed mechanical gunk that light was supposed to travel through. Yeah, that was rightly thrown out. Einstein's new ether is space-time itself. It's dynamic, it's flexible, and its structure is shaped by the matter that's in it. The big takeaway? Empty space isn't actually empty. It's got structure. Okay, so if space is this physical medium, how in the world does that explain the interference pattern? Well, the idea is that the experiment itself, the actual metal plate with the slits, it creates this invisible map of, well, pressure gradients right there in the medium. Let's try to picture this. Think of the matter of the double-slit apparatus as creating an invisible topography in the space all around it, like a pressure map. That map is the wave. It's not the particle. It's a field that exists in space before you even fire a single particle. So when you break it down, the process becomes surprisingly straightforward. First, the slits set up that invisible gradient map in space. Second, a particle comes along and goes through just one of the slits, like you'd expect. But third, and this is the key, that pre-existing map steers the particle. It guides its path. And when you do that thousands of times, well, all those guided particles build up to create that classic interference pattern. Now, I know what you might be thinking. This sounds like some grand new out-there theory. But the crazy thing is, the evidence has been staring us in the face for over 100 years. Right there, in the results of all these classic experiments. And this timeline is really the smoking gun. It started with single photons, then electrons, then to neutrons, which have no charge, and then, get this, all the way up to these absolutely enormous molecules. It just doesn't seem to matter what the particle is, what it's made of, or what its charge is. The one constant, it's always interacting with the slits. This effect seems to be totally universal. Yeah, that neutron experiment? That is huge. Neutrons have zero electric charge, so this whole thing can't be some kind of electromagnetic trick. It has to be something way more fundamental. It has to be about the particle's momentum interacting with a physical field in space, a field created by the slits. And this right here is where that old wave-particle duality idea starts to sound, well, kind of ridiculous. In 2019, scientists got this interference pattern with a single molecule made of over 2,000 atoms. Are we honestly supposed to believe that this gigantic, complex thing literally went through both slits at the same time and interfered with itself? Or is it just a little more logical to think that this single, massive particle was just following a pre-existing roadmap in space?
Oh, and it gets better. This model also gives us this incredibly simple and elegant solution to that other great quantum mystery, the observer effect. You know the one. Why does putting a detector at one of the slits make the cool interference pattern just disappear?
Okay, so in the standard experiment, without any detectors, the two slits are pretty much the only things shaping that little patch of space. They create a nice, clean, stable gradient map. And that clean map is what guides the particles into that familiar interference pattern. But here's the thing. A detector isn't some magical, abstract observer. It's a hunk of matter. It's a physical object. The moment you stick it into the experiment, you've completely changed the layout of matter in that space. And that change instantly messes up the original gradient map. It scrambles it, creating a totally different one, a map that doesn't produce an interference pattern anymore.
So the takeaway here is absolutely crucial. Observing isn't some mystical mind over matter thing. It's a physical act. You're not changing the particle's behavior by looking at it. No, you are changing the physical space it has to fly through. The map changes, so the destination changes. It really is that simple.
So, where does this leave us? What does it all mean? Well, it means we might be able to bring things like causality and locality back into quantum mechanics. The universe doesn't have to be spooky or weird. It just has to have structure.
All right, let's just recap the core ideas here. Empty space, not actually empty. It's a physical medium, just like Einstein said back in 1920. Its structure is basically a map of gradients created by matter. A particle? It always travels a single path, period. But its path is guided by that map. And that interference pattern we see on the screen, it's just the statistical result, the footprints of thousands of particles, all following the same invisible landscape.
You know, this whole model, which comes right out of an idea from Einstein that we all kind of forgot about, gives us a real, physical, and intuitive way to think about quantum's biggest mystery. It points to a universe where matter and space are tangled up in this deep, inseparable way. And that leaves us with this really tantalizing question. If these famous quantum patterns are just footprints revealing the hidden structure of space, what else is hiding right there in plain sight, just waiting for us to find a new way to look?